Alright, so now that we have a basic idea of how ions form in the first place, now we're going to take a look at how these ions come together to make ionic compounds, how we're going to represent the formulas for these things, and then also take a look at some of the properties of ionic compounds. Alright, so some general properties that ionic compounds possess. We can list those as follows. So ionic compounds generally, and again, these are general characteristics or general properties, which means we can apply them, across the spectrum for these types of compounds. So generally, they tend to be solids at room temperature. Which means then that they tend to have high melting points, MP is melting point, and also boiling points, BP. And when your ionic compounds dissolve in water, they actually end up being good conductors of electricity. So these, when dissolved in water, when we add water to our ionic compounds, they function as a substance that's able to conduct an electric current, which makes them function as something known as an electrolyte. And that means by extension is that they produce lots of ions. Right? So they actually break apart into their component ions when dissolved in water. And we're going to come back to this in the solutions chapter down the road. Alright, so those are some of the general characteristics of ionic compounds. A good example of a very common ionic compound that you may be familiar with is sodium chloride, which has the formula NaCl. We'll talk about naming and the formulas here in a little bit. Sodium chloride is more commonly known as table salt. Right, and as you know, you can sprinkle table salt on your foods, for instance, and you can, ingest a fairly moderate amount without having too much, significant consequences. However, sodium chloride is made up of sodium metal, and it's also made up of chlorine gas. So when those two things individually are very, very poisonous, you wouldn't want to eat a hunk of sodium, or you wouldn't want to breathe in some chlorine gas. But when you bring them together and you make this compound called sodium chloride, the product here is very different than either of those individual elements singly. All right, so let's see how this ionic compound of sodium chloride, and by extension other ionic compounds, can form in the first place. So when we start putting our ions together in ionic compounds, we're going to represent these in what's known as a chemical formula, where we're going to write the formulas for the ions involved in that compound, and we always are going to write the metal first. So the metal, and generally we can also say the cation, the positively charged thing, goes first, and then the non-metal, which is the anion, that goes second. And then we're going to use subscripts to tell us how many of each of those ions come together. All right, so one very important thing to keep in mind when it comes to writing and interpreting the chemical formulas is that the ionic compound, by definition, is overall neutral, and that means your total positive charge from your cation should equal the total negative charge from the anion. All right, so that's extremely important. All right, ionic compounds are neutral. So for example, with the sodium chloride that we looked at, when we write the formula for sodium chloride, it ends up being NaCl. So we have sodium, the metal ion goes first, and the anion, the nonmetal, goes second. And we said we're going to use subscripts. Well, when you don't see a subscript, 1 is understood to be there. So we have 1 sodium combining with 1 of the chloride anion. 1 is understood, so we can just omit those 1s and just have NaCl as the formula for sodium chloride, right? And that way the +1 from the sodium cancels out the -1 for the chloride, so we end up with our compound being overall neutral. So those subscripts we're going to use in the formula to tell us how many of those ions are involved, and what's going to tell us how many of those subscripts is going to be the fact that the total positive charge should equal the total negative charge. So for example, if we look at the combination between magnesium and chlorine, all right, we saw in the previous section that we can predict the charge in the magnesium ion. Magnesium is in group 2, so it'll form a +2 charge. And then chlorine is in group 7, it'll form a -1 charge, right? Just based on the group number on the periodic table. So in order for the magnesium +2 to cancel out the chloride -1, we would need 2 of these chlorides to give us a total of -2 that can now cancel out the +2 from the magnesium, right? So when we put these together in the right formula now, we're going to have 1 of the magnesium, right? Remember, we don't need to write the 1 in, it's understood to be there. And we're going to have 2 as a subscript for the chloride, right? And that'll be the formula for this particular combination of the magnesium ion and the chloride ion. You'll notice here when you write the chemical formula, we don't write the charges in. In the formula, right? We omit those. We just write the symbol and then the subscript that tell us the ratio of the cation to the anion. Similarly, if we look at sodium combining with sulfur, right? Again, we can predict the charges on these ions. Sodium's in group 1, it'll have a charge of +1, and then sulfur is in group 6, so it'll have a charge of -2, right? So we can also use our Lewis dot structures to predict what's going to happen in terms of the number of these ions involved, right? So sodium is in group 1, it's got 1 valence electron, and sulfur is in group 6, it's got 6 of these valence electrons. So sulfur needs 2 more electrons, and sodium can only give 1. So we need 2 of these sodiums to give 2 electrons to sulfur so that it can adopt its octet, and it ends up having now 8 valence electrons at the end. So it ends up being more stable, and we have 2 of these sodiums then that provide each 1 electron. So when we put this ratio together, right, we have 2 sodiums and we have 1 of the sulfur. So when we write that in our chemical formula, the metal goes first, we have 2 of the sodiums, and we have 1 of the sulfur. So that'll be the formula for the combination between the sodium and the sulfide. There's a shortcut that we can use for determining the chemical formulas for our ionic compounds. And I'll show you the shortcut here in this example. So here it says to write the ionic formula for the compound formed between barium and chloride. So we have Ba +2, and we have chloride, which has a -1 charge. So when we write the formula, right, the metal goes first, the nonmetal goes second. What we can do is we can take the charge on the metal, and that becomes a subscript on the nonmetal. And then the charge on the nonmetal 1 becomes a subscript on the barium. So we end up with BaCl2. Right? This shortcut is called a cross-charge method. Right? And that works all of the time in terms of determining the chemical formula for our ionic compounds. I'll give you another example here where there's maybe one more step involved if you run into a particular situation. So let's say that we had magnesium combining with oxygen. All right, we can predict the charge. Magnesium is +2. Oxygen is going to be -2. So if you write the formula, then we have the metal goes first, the non-metal second. We can do our cross-charge thing. So the 2 here, the subscript on the oxygen, and then the 2 becomes the subscript on the magnesium. Right, so you'll see that you end up with Mg2O2. Right, what you want to do in this situation is you want to get the lowest or the smallest ratio possible. So 2 to 2 is the same as 1 to 1. So we end up with MgO as your chemical formula for this combination between magnesium and oxygen. Right, so the cross charge is just a shortcut for determining the formulas. Let's take a look down here at this example. We have magnesium and the nitrogen ion, which is the nitride. So we have our Mg +2 and our nitride Mg -3. So when we write the formula, the magnesium goes first, nitrogen goes second. We can do our cross charge. The 2 on the magnesium becomes the subscript on the nitrogen. The 3 on the nitrogen becomes a subscript on the magnesium. So Mg3N2 will be the formula for that combination. All right, so that's how we come up with the formulas for our ionic compounds.